Okay, I cannot speak the organizer because I'm one of them. I cannot thank the organizer because I'm one of them, although I did virtually nothing. So instead, I will thank Lev for the organization of this beautiful conference and also for the audience who shows up after 3 days of intensive lectures and banquet with intensive wine drinking. Okay, so this talk is dedicated to my friend Yakir Aharonov, and this is topics. And Lev asked me, or all the speakers, to limit the number of problems that you discuss to a small number. So here I will discuss only 2 problems that turn out to be related. What I will do, I'll discuss the physics when we have electron on a sphere, and it will be subject to a field, a central field. In the first system, it will be subject to the field of magnetic charge. We call it magnetic monopole. And related talks are given by David Gross. And in the second system, I will study, so here the main physics is encoded by the Aharonov-Bohm effect, of course. And here, in the second system, I will study electron in the field of electric charge. And here, the main physics is encoded by the Aharonov-Casher effect. And of course, this is the continuum version that the sphere is smooth. And the solution for this problem are known for 80 years or even more. On the other hand, what is amazing is that nobody studied this problem in tight binding picture. And it appears that, and that's what I will do here. And it appears that in the tight binding picture, the physics is much richer and a bit slightly more complicated. And as a bonus, we get that in the tight binding formalism, remarkably, the 2 spectra are correlated. Very short history. So you know that in 1931, Dirac argued that if we have magnetic charge, it must be quantized. And this is a famous Dirac quantization condition. And this means that the flux, magnetic flux through a sphere, is a integer multiple of the quantum flux unit. There are millions of proofs. I want to mention a seminal paper by Wu and Yang that discuss this problem from the point of view of singular vector potential. There's a very nice review by Sidney Coleman in Eryshai lectures, and also there are some papers by Roman Jakiv that goes, even the last one is in 02, I think. In condensed matter physics, the notion of magnetic monopole, it's not new. I mean, it was considered by several authors. But first of all, let us look at the solutions of the problem. So the solution of the corresponding hydrogen atom problem was done by Igor Tamm already a few months after Dirac. And then there's a very beautiful consideration of the angular momentum algebra that shows that although the particle is spinless, it obeys angular momentum algebra of spin 1/2 particles. So this is just mention some methods that used in the solution of the problem. But in condensed matter, it appears to have been studied or used by several authors. This is famous paper by Holden, and then by Nagaosa. Recently, there's a group of Zonti in Princeton that consider these topics, and there are numerous papers about this. And the automatic reaction of a condensed matter physicist is, why don't you put it on a lattice or use tight binding model. And that's what I'll try to do now. What do I mean by this? I mean that the sites are located on a sphere, and the electron hop from site to site and obeys tight binding Hamiltonian. Here I take the graphene, the fullerene as an example, but I will also study simpler arrangements. And in this, I'll consider magnetic charge and electric charge. I want to stress that there is no electron-electron interaction, there is no disorder, no thermodynamic limit, just a spectrum of a small system. The main effort is to construct the Hamiltonian. Once the Hamiltonian is constructed, then we can sit down and just look at the spectrum and see its properties and symmetries. One may argue what is the motivation, at least for the magnetic monopole, that was not found. Okay, the importance of magnetic monopole has been stressed over and over again, but I must say that for me, the main motivation was just the beauty of the physics involved, of, if you wish, if I change the word, it's just physical beauty, and I think there need to be no more apologies. From other point of view, we can say the following. This is the spectrum of electron in a plane with perpendicular magnetic field in the continuum limit. This figure is nice, but it's a little boring. On the other hand, once we put it on the lattice, we get the beautiful picture of the Hofstadter-Hasbel butterfly. So what we have here is a spectrum of electron on a sphere in the field of monopole, in the field of a monopole. And the question is, what will happen if we put it on a tight binding? So this is a puzzle that I want to fill in the first part of my talk. The question is, how do you tight bindize the sphere? The sphere, how you put a tight binding on a sphere. And the answer is that if you want the highest symmetry, you have no choice but take small objects that all the links and all the faces are equal. And we know that there are only 5 objects like this. We call them the Platonic solids. So what I will do now, I just consider the spectrum of electron hopping on the side of this object in the field of a magnetic monopole. And the question is how to construct the phase factor to generate this Hamiltonian. I need to generate this Hamiltonian, and the question is how to construct this phase factor. Usually, what we do, we put phase or vector potential on each link, and we require that the integral or the sum will be identical for all faces, because all the faces are equal. But that doesn't work in a closed surface, because in the closed surface, you go on each link twice, and then you get 0. And how to solve this problem? We go to the paper of Wu and Yang, or we understand the Aharonov-Bohm effect in the following sense, that the phase itself over-describe electromagnetism because 2 different phases correspond to the same physical configuration. The field strength under-describe quantum electromagnetism because a given field strength corresponds to 2 different physical configurations. The important quantity is what is called by Wu and Yang a non-integrable phase factor, or we call them just phase factor. So let us look at the tetrahedron. If we put a flux phi on each link, on each horizontal link, then we get, we put a phase vector potential phi. Then on each phase we get flux phi, and on the basis we get flux minus 3 phi. And of course, phi is not equal to minus 3 phi. On the other hand, if we look at the phase factor, we can guarantee that e to the I phi will be equal to e minus 3 I phi if the phase is quantized. So that is, in fact, put it in another language, the lattice version regularizes the singularity of the vector potential, or in other words, it is better to work in the group elements instead of the algebra. But in any case, we have suggestions how to construct the Hamiltonian, and after we do this, we can say, now what is rest is to diagonalize it and look at the spectrum. And that's what I will do now. So what we see here is 2 Landau levels, if you wish, 2 Landau levels of electron on the site of tetrahedron in the field of magnetic monopoles, and n is a monopole number, and the spectrum is periodic in n, where the period is a number of phases. And I did here 2 periods just for the completeness. This is rather boring, so let us first connect this, and then let us check the pattern of degeneracy. And the pattern of degeneracy is a little bit intriguing, because what we see is that the levels jump from the energy jump from one level to the other. So, for example, here the degeneracy is 3, and here the degeneracy is 1. That is for n equals 0, and for n equals 1, the degeneracy here is 2, and the degeneracy here is 2. So the level pattern, the degeneracy pattern depends on the number n. And then we go to other objects. This is a cube, for example. And now you know the pattern. So this is n. The periodicity is 6. The cube has 6 faces. The periodicity is 6. And this is a degeneracy pattern. You see that in the case of the cube, there is a symmetry between plus e and minus e. And I give here what I call EGS. EGS is exercise for the graduate student. And the question is why only for the cube the spectrum is symmetric. This is an octahedron. And as you notice, all the numbers are calculated analytically. The energies are very nice algebraic number. And the matrix here is 8 by 8. We go further to the icosahedron. This is a matrix of 20 by 20, but still we can get algebraic number. If you see something like this, a square root of 13 or something like this, I have never seen it in physics, but here it appears. And also all the degeneracy pattern here. And finally, this is a icosahedron. Again, all these numbers are analytic and algebraic. And if we go back to the pattern of degeneracy, then I just draw here how many combinations you can reach the number 12. And these are just the dimension of the irreducible representation of the point group of this object. And they change with n because besides the central force that is supplied by the magnetic charge, we have, of course, angular momentum part, and also we have magnetic rotation group. And I didn't have time to analyze it, so anybody who's willing to do it is invited. So if we speak about similarity to some animal, this is a Hofstadter butterfly, Hofstadter-Asbel butterfly, and this is our flying bat. We just changed the 2 words, and this is our flying bat. Okay, Fulleren. Fulleren, it's a little bit more complicated, and designing of the phase factor is really a challenge. It requires some non-trivial concept in graph theory that is called spanning tree. You have to put the graph on the plane. You have also in the Fulleren, you have 2 incommensurate faces, the pentagon and the hexagon. And here is another EGS exercise for the graduate student to prove that the cosinus of the spherical angle of the pentagon is given by this and this for the hexagon. Anyhow, because the two faces are not orthogonal, are not commensurate, then there will be no periodicity, and the spectrum is a little bit strange or disorder. But here we have the monopole number up to 300, and this is the energy. What is interesting to see here is what I call magic number. Why do we have magic number? In the magic number, the energies are high, and the reason is that the ratio between the area, spherical area of the hexagon and the pentagon is about 3 to 2, and when we have 84 monopoles, then the corresponding flux are close to integer. It is 2 for the pentagon and 3 for the hexagon, and then we get magic number. And there are other magic numbers that can be. So by this, I finished the first part, namely electron on the sphere in the field of magnetic monopole in the tight binding model. How much I left? 10 minutes. 10? Okay. Now I do the second problem. I take off the magnetic charge and put electric charge. Electric charge, what it can do, the only thing, if the electron is confined to a sphere, then we have the spin-orbit interaction, and it leads, and the underlying physics is governed by Aharonov-Casher effect. Of course, when the model is continuum, namely I have a continuous sphere, I just get the old faithful atomic L dot S. And the question is what happens if I put it on the tight binding? And here we are not very far from experiment, because it is possible to implant ions in the derivative of the Fullerene, and this is already close to experiment what we are trying to do. The question is what is a tight binding analog of the atomic L dot S? And we see that up to alpha square, well, alpha is the strength of the spin-orbit interaction, we can write the Pauli equation in this form. So look, and that is related to the talk of Schneermann, that we see the complete analogy between the U1 and the SU2 part of the Hamiltonian. In fact, there is a seminal paper by Fröhlich and Studer that use this idea to argue that the Pauli equation has approximate U1 SU2 symmetry. So this helps us to construct the hopping term. Without going to details, I would say that we have 3 elements here. We have elements that I call mu, which is the strength of the spin-orbit interaction. Here the physics is encoded by this. We have a vector Nij, which is perpendicular to the plane defined by the center of the object and the 2 adjacent sides. And we have, of course, the angle theta that, of this triangle. And therefore, the hopping term is built by this SU2 matrix. And after we do this, we constructed the Hamiltonian. And again, we are looking at the picture of the spectrum. So this is the spectrum of the tetrahedral. What we show here, this is the strength of the spin-orbit interaction, and this is the energy. And of course, here we do not have any quantization, so we just, the spectrum is continuous. And it has some interesting properties, like it has, first of all, Kramer degeneracy, because the system conserves time reversal invariance, but it has also 2 symmetry points, interesting, that are not trivial. One is when the mu equals theta half, and again, why is that remarkable? Because the mu is a physical quantity, is the strength of the spin-orbit interaction, and theta is a geometrical quantity. And at this point, we have a symmetry, and then we have another symmetry point related to this equality. All this is, can be proved, and then let us see, this is a cube. The matrix is 16 by 16, but still we can get analytic results for all the energies, and you see that the symmetry point all the time exact. This is an octahedron, matrix 12 by 12. This is a icosahedron. The matrix is 24 by 24, and still we get a result. And finally, even for the dodecahedron, where the matrix is 40 by 40, we still can get analytical result, although two eigenvalues are needed to, we need to solve quartic equation in order to get them. And here we show all the levels, and these levels are a solution of this. So these are more complicated eigenvalues, and they are six-fold degenerate. And finally, even in the Fuller-N, which we cannot have analytic solution, but you see the symmetry lines here and here. So by this, I finish the second part, namely electron in the field of electric charge in the tight binding model, where the physics is governed by Aharonov-Casher effect. And now, just 5 minutes or even less, before we wanted to submit to back-to-back paper, we noticed an amazing property, that the spectrum of the electric system at the symmetry point is exactly equal to the spectrum of the magnetic system with n equal 1. Exactly, not approximately. I mean, this and these are exact number. And that is rather strange, because the two systems are different. Again, this conserves time reversal, and this is not. Here the spin plays important role, and here is not. Here the dimension is 2v times 2v, where v is the number of sides, and here the dimension is only v. And still we get exact correspond between the spectra, and that's what I call Aharonov-Bohm mit Aharonov-Casher. And the reason is related to the spherical geometry. We can show that at this and only at this point, we can have a similarity transformation of the spin orbit Hamiltonian, which looks like this. So you see it's H1 and H1 complex. Therefore, the 2v by 2v Hamiltonian conserve time reversal, but each one does not. And then we inspect the hopping term of this H1, and we find that these hopping terms are phase factors, and the cosinus of this omega AB are just two adjacent points, and the cosinus of this is given by this formula. It contains the angle theta that I showed you before, and also the spherical angle of A and B. And I don't know if this formula reminds you of something. Is something understand what this formula means? Okay, this is a Heron formula for a spherical triangle. What is Heron formula? Heron formula gives you the area of triangle if you know the length of its sides. And there's a Heron formula for Euclidean triangle, and there's a Heron formula for a spherical triangle. And this is one of the versions of the Heron formula for the spherical triangle containing the point AB and the North Pole. What is the upshot? The upshot that when we multiply all the phase factors, we just get the area of the sphere. And if you get the area of the sphere, this is exactly the magnetic flux of the unit magnetic monopole in unit of the flux quantum. So in this case, there's a nice game between physics and geometry that gives us this picture. And if you want, you can say that one of the consequences is that you can guess the spectrum of a system that is experimentally inaccessible. This is a system with a magnetic monopole. You can guess it by the system of the electric system, which principally is experimentally accessible. Okay, so what you take home instead of summary, first of all, we have a beautiful spectrum here, the flying bat. We have interesting structure of point groups that must include also the angular momentum of the magnetic monopole and the magnetic rotation group. We have magic number in the Fullerene. We have a suggestion for the tight binding analog of the atomic L.S. And we have a correlation between two spectra of seemingly different systems where AB meet AC. Okay, thank you very much for your attention. And in this reference, there is, at least in the first one, there is a useful appendix on Fullerene that we couldn't find elsewhere. So if somebody interested in the geometry of Fullerene, he may consult this reference. Yeah.
Well, that was indeed a beautiful illustration of physics in beauty in physics. Thank you very much.
Thank you very much.
Are there any questions? Sam?
I noticed you get in your energy spectrum both for the dodecahedron and also for the Fullerene, because they all involve pentagons.
Yes. No, Fullerene is 12 pentagon and 20 hexagon.
Right. Yeah.
Yes.
But they involve the square root of 5 minus 1 over 2 everywhere. The golden ratio is everywhere in those energies.
No, it's square root of 5, but not exactly square root of 5 minus 1 divided by 2, I think. You have a lot of square root of 5.
I thought I saw it numerous times.
Okay. Mm-hmm.
Isn't true?
Yeah, somewhere it appears, but not. It's not ubiquitous. Yes.
Yeah.
Okay. So what is the question?
Yeah. Somehow the symmetry of the pentagon. Here we go.
Mm-hmm.
A lot of square root of 5s.
Yeah, a lot of square root of 5. But if you find the golden mean, yeah.
We thought it
The
was
Fullerene, I thought.
Yeah, maybe. Yeah, you can take square root of 5 away. Okay.
All right.
Maybe it appears there.
The
Yeah.
golden ratio occurs in here also. So
Okay.
there's geometry everywhere.
Yeah. Yeah. Exactly.
Questions?
Pavel, no?
Yes, I had a question. First of all, as usual, I make a remark.
I didn't hear you.
As usual, I make a remark.
Mm-hmm.
Truly beautiful.
Really?
Yeah. And
Thank you very much indeed.
The question is, you mentioned an approximate SU2 plus 1.
Yeah.
What do you mean
Ah.
by approximate?
I mean,
Definition of
okay. I mean that the Pauli equation involves only the cross term between the momentum and the sigma cross E. What I did, I completed the square, and I neglected the square, the other things.
Okay. This is what you mean. All right. Got it.
Yes, question there. Okay.
I'm not sure the tight binding is absolutely needed for this kind of thing. I'm not sure exactly.
Absolutely?
Needed, necessary.
Well, no. I mean, it is just a model. It's just a model.
One uses
To the results that I mentioned, yes. Because there's no thermodynamic limit here and so on, it is really needed. I don't know what happens in the thermodynamic limit. It appears that you can try to do derivative of Fullerene with a larger and larger number of hexagon and always 12 pentagon, and to see if you get spectrum similar to graphene or something like this. The answer is no. At least in the Fullerene case, we didn't have any zero mode. Namely, there was no solution, zero energy. Like you have in the graphene, you have zero energy lambda level. Here we don't have zero mode.
If there are no other questions, let's thank all the speakers from this morning's session.